Good afternoon, everyone. So today is the week 12 interaction session on structural vibration. So we have at the end of this course. So today, what I plan, like we will revisit the complete multi-degree of freedom system, and we will solve all kind of problems which you know uh, can come your final examination, and also we will solve different kind of problems related to your current week assignments that will help you to solve the current week assignments also. And uh, I also scheduled one extra class as per your request, so that we can discuss all kind of questions, um, like starting from the beginning. So today, what we will do, we will stick to the multi-degree of freedom system. So we will revisit that how we can formulate the equation of motion, then how to solve it, different kind of problems, different kind of problems related to Rayleigh and Caugh damping model. Then we will move to force vibration. We will see how we can solve these problems, different kind of problems, like MCQ, MSQ, and different kind of numerical problems. Okay, so we will try to solve it. Okay, so let's quickly start today's session, because today we will going to solve a hell lot of problems, so it will take time. So uh, we already have discussed about the multi-degree of freedom system. We have the basic knowledge about it, and now we are in a position that we can now solve this kind of systems easily, right? So let's quickly talk about little bit about this systems, and then we will move to the problems. Okay, so multi-degree of freedom system. So first, let's talk about like degrees of freedom. What was the definition of degrees of freedom? So it says like the number of independent displacement coordinates required to identify position of the displaced mass, or position of the mass with respect to its original position, right? So here we can see that we know that this is a frame model, and we have idealized it to spring mass damper system, where we have considered the viscous damping model, and for the multi-degree of freedom system we will discuss different kind of damping models too. So here you can see we have two masses. So to describe the relative position of these masses, we need 2 degrees of freedom. So here we have considered that x1 and x2 will be the 2 degrees of freedom corresponding to these two masses, right? And for the MDOF system, the external force may act on each degrees of freedom, or specifically for a particular degrees of freedom it may act, and we have seen how we can uh, uh, encounter and solve this kind of problems. So first, what we need to do, like MDF system, we have solved for free vibration cases, and we have solved for the force vibration cases. Okay. So nonetheless, today what we are actually, what I have planned, like we will go through the complete MDF system. We will solve different kind of problems. Okay, and the problems also related to your current assignments. So instead of doing finite element coding, I feel that if you stick to the problem solving more, then it will be more helpful for you to understand which kind of problem can come and how to deal with them, right?
You are right, sir.
Yeah, so today we will stick to the MDF system, the complete MDF system, and like 14th we will solve SDF system and different kind of problems which we feel that okay, we need to include it. I will include them. Okay, so
Fine, fine.
Yeah. So let's quickly revisit that things little bit. The main parts, the equation which you need to remember, that things we will touch upon. Then we will go to the problems. Okay. So we have seen that if there is a multi-body system, we can develop the equation of motion either using free body diagram approach or the energy approach. So we have solved in both the approaches, but if you stick to one approach like free body diagram approach, you can also formulate the equation of motion. So here for the 2 degree of freedom system, here x1t and x2t are the 2 degrees of freedom corresponding to two masses, and consider that okay, in each degrees of freedom there is a forcing function acting on it. So first one is f1t and the second one is f2t. Now we need to formulate the equation of motion. So what do we need to do? We need to make the free body diagram. So first we have cut this section with respect to m1 and m2, and all these forces and the relative displacement we have figured it out, and from these two masses we have found out two equations. Equation number one for this mass one, and equation number two for the mass two. So we can easily formulate it. If we look at this free body diagram, we can easily sum them up. Like here, whatever is done, summation of fx taken as 0, and by this way we have formulated these equations. And after that, when we combine these two equations, we will get the coupled equation of motion, right? If you combine these two equations in a matrix form, so what will we get? We will get this term m1 m2 x1 double dot. Either you can take the degrees of freedom as x of t, or the responses or u of t, both are the same. So during the course, few times I have used that x of t, and many times I have used u of t, both are same. You can stick with one notation for the uniformity. Okay, so here you can see in our C matrix particularly and the K matrix are coupled, right? Now what we need to do? So to derive the responses of this system, we need to solve this coupled equation of motion. In a way, we need to decouple it, right? And we took the or we have the leverage to use that eigen operation to separate them. So how we formulate that characteristic equation to solve them using eigen equation? It was quite similar to your SDF systems. Like here, first we need to consider that undamped free vibration case, and from where we have solved for the natural frequencies and the mode shapes, right? So we have the equation of motion m u double dot plus, we are considering the undamped case. So the damping, for the time being, the damping will not be there, but we have seen how we can incorporate different damping models like Rayleigh damping, Caugh damping, and all these things. So we will come to it later, little later. So u is equals to 0. So free vibration case, obviously no external forces will acting on this system. So we need to solve this system in a way, or we need to decouple this system in a way, like we will get the natural frequencies in terms of like eigenvalues and the mode set in terms of the eigenvectors, right? So for that, what we have done, we considered a general solution. U of t is nothing but u e to the power, like a one harmonic u e to the power I omega t, where u is the amplitude of this vibration and omega was the frequency of this vibration or the harmonics. Now if you double integrate this, double derivative this, you will get omega minus u omega n square e to the power I omega n t. Now these two, if we put back into this equation, equation number 2, or this equation whatever we have formed here, so what we will get? We will get this minus m u omega square plus k u e to the power I omega t is equals to 0. Now, obviously, it's a dynamic system. There should be some initial conditions. Either the system, the vibration can start from the absolute 0, or maybe there can be some initial condition. So we are talking about free vibration case, and we know that free vibration actually initiated with some initial condition, providing some initial velocity or providing some initial displacement. So we need to look into the initial condition. So let's say these are the initial displacement for these 2 degrees of freedom, and these are the initial velocities for 2 degrees of freedom. Now we can easily work out with this equation very easily. So if we further simplify this equation, what we left with? We left with minus mu omega n square e to the power I omega t is equals to 0. Now this part e to the power I omega t or omega n t cannot be 0, because we have taken this as one of the solution for this equation of motion. So what we left with? We left with this equation, minus m omega square plus k u is equals to 0. Now u, that are the responses that cannot be 0. That means we must have the inverse of this portion should be existed. This cannot be 0. If that is 0, then u will be 0. That means we will not have any kind of responses. So what we need to do? We need to make this equation is equals to 0. That k minus omega square m is equals to 0. Now this equation is called the characteristic equation or the frequency equation for this multibody system. Now, and one more u will be there. So if you look at this equation, this comes as a form of the characteristic equation for the eigenvalue problem. Like you can directly correlate this with AV is equals to lambda V. What is this equation? This equation is for the eigen values and for the eigen operation more precisely. So what we call the eigen vectors or eigen values? Precise definition. Nandalal, can you define them? Whom we call eigenvectors and whom we call eigenvalues with respect to mathematics, linear mathematics. Yeah, please try it. Are you there? Okay, so I will explain. Uh, you are actually unmuted. Nandalal, are you there? Well, no issue. So eigenvectors, actually in mathematics, the eigenvectors are the non-zero vectors. Now, once we apply the linear transformation to these non-zero vectors, apply any linear transformation to this vector, these vectors can either shrink or stretch, right? At most. So these non-zero vectors are called the eigenvectors. And the scaling factor, what I said, that if we apply any linear transformation to them, that will either shrink or stretch with a scaling factor lambda. And this scaling factor is called eigenvalues. So look at this equation. This is the linear transformation A applied to this non-zero vector. What happened? This vector remain this, but this can either shrink or stretch. These values we call eigenvalues. So it's a one kind of decoupling process. Instead of this, we can use also Cholesky decomposition, but we haven't covered this for these courses. So once we have this formulation, we can easily, figure it out our equation. So what we need to do, we just need to equate the determinant of this characteristic equation to 0. Then we need to look for the roots. So we will have these roots plus minus omega 1 square and plus minus omega 2 square, right? These are the eigen values, that lambdas, right? After solving, if we consider them with respect to the mathematical formulation, this will be the values. Now with respect to lambda with respect to these frequencies, what do we need to do? So we have lambda 1 and lambda 2, that means corresponding to omega 1 and omega 2, or omega 1 square and omega 2 square. Now what do we need to do? We need to find out the corresponding eigenvectors, whom like the further we have defined them as mode shapes. So first we need to find out with respect to omega 1 square first root, and then second we need to find out these vectors with respect to the second frequency square, omega 2 square. So easily we can form it like k minus omega 1 square in the characteristic equation. Instead of omega, first put the first root value multiplied by a vector is equals to 0. Now this phi 1 is the, we call the first mode, which contain phi 1 1 and phi 2 1, right? And the also the structure of a mode shape, how we can write it down, phi 1 1 phi 2 2, already I have discussed, also I will touch upon today also. So for the second mode also we can do like this, and we can find out these vectors. So we have now our omega 1 omega 2 and corresponding phi 1 and phi 2 mode shapes. So in a way we have decoupled this equation. Now we can sort it out. So from this type of question, one or two or multiple question may come from here, from the characteristic equation, find out the mode shape, normalize the mode shape, and all these things. So how you can tackle this kind of things, like say for example here, look at this problem here for this two-story building. One tips for me, like for the MDOF system, for 2 DOF and for 3 DOF system, you must remember the structure of the K matrix and the C matrix. That will be very helpful during the examination. Otherwise, like you need to think of what should be the format of the, or the flow of the matrices, or might be you will end up with wrong answers. So for this system, let's quickly solve it. Here today our system is given. Mass M1 is given as 9 kg, and M2 is given as like 1 kg, and corresponding K1 and K2 are given. So first what we need to do, if this kind of system is given, first you just form the M K matrices, right? So A matrix we can easily found out, like it's a diagonal matrix. We know for a 2 degree of freedom system it will be M1 and M2 diagonal, and other terms will be 0. And for the K matrix, similarly K1 plus K2 minus K2 minus K2 and K2. So now we have these two matrices. Now what we need to do, you need to solve the characteristic equation, determinant of this, and find out the root of the equation. That means you will find out what will be the value of omega 1 square, what will be the value of omega 2 square. So here this equation is quite straightforward. You just, what you need to do, just multiply this minus multiply with this. So finally we have found out this equation, and the root of this equation are these two, right? So how we can solve, or how you can easily or within time you can solve this equation. Small equation will be given like this, omega to the power 4 minus 6 omega square plus 8. You need to solve it, like what should be the omega 1 square and what should be the omega 2 square, and consecutive different kind of problems will be there related to that problem. I mean, if your omega 1 and omega 2 calculation will be wrong, then rest of the questions will also get wrong. Okay, so be careful with the first part. If you needed time, pay time with this part and then move forward. Okay, so Bob, what actually we are doing today, is like we are revisiting the MDOF system, and try to solve all the problems related to the MDOF system, which will be helpful for your examination. Uh, Along with the problems which are in your assignments, current week assignments, all the problems are there. Just watch the video carefully, or just pay attention here. You will understand all the things. So today we will stick to that, and on 14th we will stick to other SDF system and the related problems. Whatever we left today, we will address them. Right?
All right. Okay. Thank you.
Okay. So the approaches also, you need to understand the approaches, how you can solve it quickly. Like this equation, this matrix, you need to solve it using your on-screen calculator. So get habituated with that, right? So eigenvalues, once we have found out these frequencies, we can easily find out what will be the corresponding mode shapes corresponding to these two frequencies. How? Again, you need to for that use that characteristic equation for the first natural frequency, like k minus omega square m. So we have now k matrix, we have now m matrix, we have now the value of omega square multiplied by phi 1. So that phi 1 actually content, that means the first mode shape phi 1 1 and phi 2 1. That means the structure of this phi n, if I say this is phi first mode shape, that will contain phi, say, first degree of freedom, first mode, then phi second degree of freedom, first mode. That is the structure of this mode shape. So I will describe it later also once we will have this complete modal matrix. So these are the actual structures. Someone write like this also, like phi 1, they prefer writing phi 2 1 first and then phi 1 1. That means for a building like this, if this is your phi 1 1, this will be your phi 2 1. So like as per the structure, they prefer to writing it, or in a way if you write in this format, this is also okay, because this directly defined or denotes this is the ordinate related to your second degrees of freedom, right? So first what we need to do, you need to formulate this equation, and you will have these two equations. Now you need to solve it. So here we have four unknowns. What we need to do, first we need to consider or normalize the last ordinate or the last degrees of freedom to 1, generally the last one. So here the last one is phi to 1, so we consider that phi to 1 is equals to 1. So easily now from these equations we can easily figure it out what will be the value of phi 1 1. So phi 1 1 will comes as 1 by 3. So first mode shape has formulated, this is content 1 by 3. If we write this format, it will look like this 1 and 1 by 3, and if we write it in that format, it will look like 1 by 3 and 1. That means that 2 1, you need to first define, okay, in which format these mode shapes are given. First you need to find it out, like always the last ordinate corresponding to the last degrees of freedom, they we normalize it to 1. So we have seen the mass normalization, the amplitude normalization, all these things, and these things also are very important, like mode shapes will be given, mass matrix will be given, and they will ask find out what will be the mass normalized mode shapes. I will show you that kind of problems also. So second mode shape, similar way we can find figure it out for the second mode shape also. And now similarly we can we can draw them. So this is the structure, actual structure or actual 2-DOF system. Our first natural frequency omega 1 square comes as 2, and omega 2 square comes as 4. So corresponding to omega 1 square is equals to 2, this will be the mode shape, and for corresponding 4, this will be the mode shape. Now this kind of question, pay attention, like this kind of questions, uh, for this they will say like there are 3-DOF system or 2-DOF system. Let's say stick to the 2-DOF system, they will not go beyond 2-DOF system. So 2-DOF system will given. So they will say this is your u1, u2, and the mode shape also will be given, like 1 by 3 and 1, or maybe like this minus 1 by 3 and 1. Only the mode shape vectors will be given, like phi 1 will be this, phi 2 will be this, and different kind of pictures will be given. So correlate what will be the first mode. That ordinate will not be given, but the structure, the what will be the deflection pattern, that will be given. So you need to identify which should be the second mode, which one is the first mode, and all these things. Get my point? Okay, so now let's quickly talk about like mode shapes and modal representations. So what is mode shape? We already have the definition of the mode shape. It's nothing but the deflection pattern. So this is the real structure. These are to the deflection pattern related to the frequency omega 1 and related to the frequency omega 2. So mode shapes are nothing but the deflection pattern of a structure related to a particular natural frequency, or we can say it is nothing but the time frozen screenshots of the displacement response of a structure. and basically they doesn't depend upon the force or loading condition. They only depends upon the inherent properties of the structure, like when the frequency will change, then only it will change. So few basic concepts from the mode shapes you need to recall. And for the modal representation, when we form the total mode shape matrix, just recall how we form it. That phi, this is the modal matrix. That means it contains all the mode shape information related to that structure, right? So the uh, construction or the structure of the layout of this phi matrix is generally make like this: phi, j, and n. This j denotes the number of DOF and n is the mode number. So here you can see phi 11, phi 21, and phi n1. That means this complete column will define the first mode shape phi 1. Similarly, look at this phi 12, phi 22, phi n2. That will tells you about the second mode shape phi 2. Similarly, we can combine all the modes in a one matrix, and we call the modal matrix, right? Similarly, we have seen for the spatial matrix, that means all the frequency values we can combined in one matrix, and this matrix becomes the diagonal matrix, because already we have done the eigen operation, so we left with the diagonal matrix, and this is called your spectral matrix. Okay, so in spectral matrix, all the diagonal component actually denotes the natural frequencies of the structure, right? So if a spectral matrix is given like the spectral matrix of a structure or of a 3-DOF system is given like this, what should be the natural frequency of this system? For 1 mark question, it will be easy. So now, like we have some properties of these modes, like they are orthogonal to each other and orthonormal to each other. That means once we have multiplied phi n transpose like phi n, that should be equals to 1, but phi n transpose phi m, if m not equals to n, that will be 0. And also we have seen that to make the k and m matrix diagonal, what we need to do, we need to multiply with the mode shapes to make them orthogonal. So the orthogonal property also you need to know. So kn, that means the mode shape normalized stiffness matrix, and this kn is nothing but the nth component of the total k matrix. So nth component. So how we can get it? Phi n transpose k phi n. And for you know normalized mass matrix, say m or phi n transpose m phi n. If we want to take the values of each component, that means m n, this denotes the nth component of the mass matrix. So how we can find it out? It's nothing but particular mode, nth mode, phi n transpose m phi n, and here phi n, that is the total modal matrix, and that will the value will comes as a identity matrix. Already we have seen it. Now here also that kn, very useful equation which you need to recall, like kn, that means the normalized stiffness matrix, or more precisely we can say the element of the normalized stiffness matrix, the elements of the normalized stiffness matrix. So elements of the normalized stiffness matrix, how we can find it out? Or the nth element, more precisely nth element of the normalized stiffness matrix. So here we can say that phi n transpose k phi n, right? And we know that k is nothing but omega square m. So ultimately what we left with, that kn is equals to omega square mn. Very useful relation. And I'm pretty sure we are using that relation, there will be questions. Okay. So just remember this. Like which kind of question? The kn matrix, mn matrix will be given. What you need to do, you need to find out the omega. You can easily find it out, just need to do the inversion or the calculation. Or omega and mn will be given. They will ask what should be the normalized stiffness matrix for this particular case or for the particular node, right? Now we have seen other normalization of the particular modes. So first we have seen the how we can normalize it to unity. It's simple, like how we can normalize a vector. If we have a vector, say for example, if we have a u vector, okay, it has some coordinate, how we can normalize it. So normalization, to normalization, what you need to do, you say for example u1, the normalized one will be u1, the vector itself, divided by the Euclidean norm of u1. That means it will gives you the normalization of this modes. So if we want to normalize it to 1, we can easily do it. Or already we have seen, like take if I directly coming from the characteristic equation, what you need to do for the last ordinate,
So
you
it is
need to
like
take,
a unit vector.
yeah,
It is like a unit vector, though.
yeah, it's like a unit vector, exactly. In mathematics, like a unit vector, how we made some vector to unity, that's all. That's all only. Yeah. So like here we have u1 is like that, how we can normalize to unity. You just need to, divide it to the Euclidean norm of this. Euclidean norm is nothing but the square. So vectors we cannot make the square, so what we need to do, u1 transpose u1 transpose and u. By this way we can make the calculations, right? So this kind of short type of question, like the u1 vector is given to you, or they said like mode shape is given to you in a vector form, in a way like 1 by 3 and 1, right? So they asked normalize it to unity. What should be the unit normalization or normalization of mode shape if we want to normalize it to unity, right? So how you can do it, you just need to you know this vector u1. So in a transpose form, how we write 1 by 3 and 1, just uh, recall the structure of this formulations, right? Now you just need to do the calculation. So this one is very quite easy. So you just need to multiply this with this, plus multiply this with this, and you just need to divide it. So you will left with this will be your normalized to unit mode shapes. So instead of like this u1, they will ask, okay, phi 1 is given as that, कोई भी एक value दे देगा. Now they will ask normalize to unity, and what will be the answer. Get it, how you need to, how you can solve it. So practice, you need to practice it, okay? Otherwise this 1 minute problem will cost you 3 or 4 minutes or more. Great. Now, we have seen the amplitude normalization also. For the amplitude normalization, what you need to do, what already I have said, that for the last ordinate, you just need to take one and you do this to equate it and make the formulation. So amplitude normalization is not that much of interest of any engineering dynamics. Rather, mass normalization is very important thing. How we can do the mass normalization thing. So for the mass normalization, and this mass normalization actually things actually makes like computational easy. Like when we will see the computational time or the effort we need to put in without mass normalization mode shapes for the calculation purpose, we have seen that if we go with the mass normalization part, that computational effort will require less. So here we can see that if we want to make any of the element normalize with the mode shape or the mass normalized mode shape, so what do we need to do, phi n transpose m phi n, right? That will be n. And ultimately, if these are the mass normalized mode shape, then this will become 1. So phi n transpose k phi n also will become 1 if these are mass normalized. So how we can do the mass normalization thing? So we need to consider it to 1 and then do the calculation. So I will show you some problems how we can do the mass normalization things, because we need to have this mn matrix at the very beginning, how we can get the mn matrix using that phi transpose m phi, and also that kn will be phi n transpose k phi n, and that will leads to your omega square into mn, and we have seen mn is equals to 1, so your kn will become omega square. Got my point? This is very important relation, very important relation. Say for example, for a two DOF system, for a two DOF system, They will give you the mass normalized mode shape. This one is phi 1, this one is phi 2. They will give you the K matrix also, right? Now they will ask what should be the value of omega. How you can find it out? You just need to find out Kn, that means phi n transpose K phi n, and this will give you the omega value, because already we have established the relation, or already we have seen the relation. So this relation also important. One question will definitely come from here. So continuing with the problems, let's say we have another problems, and let's figure it out how quickly we can solve it, like using the calculator, on screen calculator, right? So a two-story building, the floor mass are given, stiffnesses are given, and calculate the frequencies for two modes. That means first what you need to do, first you need to form the M matrix. So M matrix, that's why I am telling you, like for the 2 DOF and for the 3 DOF system, please remember the, you know, structure of the M and K matrix. So what was the, for the 2 DOF system, what is the structure of a K matrix? Please tell. What is the structure of K matrix?
K1 plus K2, then K2 minus K2, K2, K1, sir.
Yeah. So quickly, very quickly, you need to form this equation, this characteristic equation. Now you need to solve this characteristic equation. Like what was our value? So the values are like this, like 7600 minus 3400 minus 3400 3400 and some 10 to the power 3 minus omega square into the M matrix 2200 is equals to 0, the determinant of this. Now your task is to like form this equation. Now solve it. How much time it's required to solve this characteristic equation to get omega 1 and omega 2, you need to figure it out for any problem. Like this kind of problem, the previous problem is also similar. So what I recommend, please take one of this problem and solve it until you get some way to solve them, easily, using that scenarios, like you have only pen and paper and the on-screen calculator. How you can figure it out? You just need to recall. Otherwise, like
Hello.
yeah, Bob.
Yes. In forming the stiffening matrix, you multiply by two. Is it because it is two modes?
Multiplied by 2 means
Two times into bracket. You see, when forming the K matrix, you form the K matrix, but you multiply it by two. I can see two times, two times, two times, two times.
2 times 2 times. Oh,
See,
this one.
two,
Two,
this
two,
two.
two, two.
Yes.
uh okay, so that should not be 2 by, because minus k2. So just please go through the calculations. Minus k to 2 will be not there. 2 2 2 2, why I multiplied over 2? You don't need to multiply over 2, because already given na k1 is given, so you don't need to multiply it with 2. Just correct the calculations. Okay.
All right. Okay. Thank
Okay,
you.
the stiffness of each column K1 and K2. Stiffness of each column is K1 and K2. Oh, okay. Why I multiplied it 2? Because oh, because no, you need to multiply it with 2. Here for this system, for each column, the K1 is given for each column 2100. So we have two columns here. So the question should be formulated like this. So the question is incomplete actually, because here for each column, not for the total stiffness of the column is given. So for the each column, if we consider there are two column, I've considered it like it, if there is two column. So what will be the final value of K1? The final value of K1 should be 2 into this value. Na? That's why 2 comes here, Bob.
Okay. Good. Good.
Okay.
So if it is three, you go in that order. Right.
Yeah. Because there are
Thank you.
two, columns are there, but this problem should be like this. Either the picture or the drawing should be there, indicating okay K1 and K2 both on the side, and then put it like this, or they can use like this one, like mm, here. for K1 and K2 already given the total value of K1 and K2 here.
All
Okay.
right. Okay. All right. Thank you.
But this kind of conflict will not be there in your final exam, don't worry. But yes, very good point you have highlighted. Like if the stiffness of each column is given and we have like two DOF system, so for each story you need to consider it multiplied by 2, right? If that each column is like this word is there, get it? Okay. So the main point is to solve this characteristic equation. You need to figure it out how quickly you can solve it. Because just stay with me. I will show you series of questions which are connected, and most likely this kind of question will come. On the 14th, I will show you like what should be the structure of MCQ, how many MCQs will be there, what should be the structure of MSQs, how many MSQs will be there, what should be the structure of the numerical problem like 1 marks, 2 marks and 3 marks. So most likely the 3 marks question will contain this kind of problems. Okay. So just few things you need to recall today, and you need to practice with respect to or in contrast with the MDOF system, like this how we can solve the characteristic equation. So it's nothing but you just need to solve this k minus omega square m. This means this equation this nice long equation. You need to find out omega 1 and omega 2. And one more tips, like to this you just can use the root finding formula. Okay. Minus b plus minus root over 4ab by twice a, that formula.
Yeah, the quadratic.
Yeah, so that will be more helpful than solving in root using calculator. Like how we solve it, we use MATLAB, or we directly feed the equation to the calculator and calculator gives us the value. But we need to Sridhar Acharya formula. We just need to use that Sridhar Acharya formula, that minus b plus minus root over 4 ac by twice a. That formula if you use, you can easily find out the root. So practice these 2 or 3 problems. I have added more problems later on. We have like total 65 slides, and total 65 slides content, each content the problem. So you just practice them. If you practice them, that will be very easy. And the kind of problems which we are discussing today, that kind of problems mostly 90% of this come from this. Like data will change, they will change the data little bit. Rest of the question, the formation of the question, the structure of the question will be same, right? So first, what we need to do, we need to find out the omega 1 and omega 2, the first two natural frequencies from this characteristic. And first hurdle here, omega 1 and omega 2. Once you find out that omega 1 and omega 2, your life will be easy to solve these questions, right? So now, again, continuation of this question, like calculate the first mode shape. They will not ask you calculate the mode shape. They will ask just calculate the first mode shape, right? Or this problem can be cast like this. Omega 1 should be given, your M matrix should be given, your K matrix should be given. If for 2 marks question, omega should be given, like omega 1 is 29.32 rad per second. Your K matrix and M matrix, they will give directly. You just don't need to formulate it. Now they will ask what should be the mode shape corresponding to it. So what you need to do, you need to again use this characteristic equation, K minus omega square m is equal to, multiplied by your phi 1 is equals to 0, and phi 1 will contain phi 1 and phi 2. So once you have this equation, you will get two equations in terms of phi 1 and phi 2. You will get two equations. Some values will be there, some values will be there, some values will be there, some values will be there. So what you need to do for to solve this, you need to consider that phi 2 to 1. That means the last ordinate of the mode shape we will take at to 1. That means we normalize the amplitude to 1. So if we consider that 2 1 is equals to 1, we can easily find out what should be the value of 1 1. We can easily calculate the equation, the mode shape. We can find out the mode shape. So look here, they have like write it down in another manner, but to write it down or to express this mode shape in that manner, what you need to do, they need to write it like this 2 1, and that will be 1 1, not like that. So that will be, to solving this you can use this, and after you just need to look for the options how they actually express it. Like phi 1 can be expressed like this: either I can get the ordinate first, and this phi 1 1 and phi 2 1. Either I can write phi 1 1 or phi 2 1 like this, or I can write it phi 2 1 and phi 1 1. Both actually represents the first mode. Great, got my point? So you should be careful with the options, how the structure of these modes are given. Clear? Great. Now, then we have seen how we can find out the physical responses using this modal representation. So that was quite easy. Like the physical response u of t is nothing but the generalized coordinate into the mode shape for this. So for the total matrix, we can easily find out that what should be the responses. U of t is nothing but that phi matrix multiplied by your generalized coordinate vectors, right? Phi, already I told you that mode shape doesn't depend on the time. It's time frozen screenshot. And this QNT is the time varying property or the responses, or we can say modal responses. We can find it out using, we have different kind of approaches. We can find out easily. So now we have solved for modal expansion, where this modal contribution, this equation is very important. What should be the modal contribution for a particular mode? So modal, in modal expansion, we can write it down like this, that the response vector u, this is vector that content u1 u2 u3, all these things. So this vector is nothing but summation of all the modes, contribution from the summation of all the modes. That means my response is nothing but, if I want to consider all the modes or the response contributed from the all the modes, that means r is equals to 1 to n phi r q r, or we can write it down as a matrix form, total phi matrix and your q vector, right? So from here we have a very important concept, or for modal contribution, what should be uh, or how much a particular mode contributing to the response, how much, or if I simplify this like this, like we have a n degrees of freedom, where n number of natural frequency and n number of modes are there. Now I am interested to find out that, okay, due to the first mode or due to the second mode, what should be the contribution of these modes to the total response. This way we can easily find it out, qn. So this qn, you need to recall the formulae for this participation factor. It's nothing but, we come from this equation, uh, like starting with the u is equals to summation r is equals to 1 to n phi n, then we have multiplied both side phi n transpose into m and simplify this equation and find out that phi n transpose m u divided by phi n transpose m phi n, and this phi n transpose m phi n is nothing but mass normalized matrix or normalized mass matrix. So you need to recall this formula. Obviously, one question or two question will come asking the modal contribution. The mode shape will be given, the mass matrix will be given. You just need to find it out. So u is the initial displacement or initial condition, that u vector will contain u0 or u1.0 and all these things. So this very important thing, you need to recall it. Like we will solve few problems related to this, like later on. I have added uh, much more problems, don't worry. So recall this, we need this formula also. Now we have solved how we can get the responses for this physical response. U vector is the mode shape matrix, like you already you have written it like this, phi matrix multiplied by q vector. So we can have this simultaneous equations. If we once we solve them, we can easily get the physical response as per the modes, right? And for the free vibration case, already we know what should be the qn, because For the free vibration case, recall we already solved like what should be the final response for the ordinates like x of t, a cos omega n t plus b sine omega n t. Like that, q n t is nothing but a cos omega n t plus b sine omega n t, and a and b we can find it out from the initial conditions. We have already seen it, and we can formulate the whole equation of motion. So from this whole equation of motion, they will not ask any kind of questions, but from the you know that small part, like if we want to solve few problems, we will go into the later, but let's solve few problems like this. Very careful, or just focus on here. What this problem says: the mass and stiffness of a MDOF system is given. M is given, K is given. The mode shape is also given. Mode shape matrix, that means the modal matrix. The force is also given. Already we have seen the force vibration case, so uh, I'm not going into that details, but let's stick to the problem session. So calculate the mass normalized mode shape. Mass normalized mode shapes. How we can do it? Mass normalized mode shape. So first, what we need to do, already we have discussed. Like first, we need to calculate what is the mass or what is the normalized mass matrix with respect to this mode. So what we need to do? M. We need to find out this MN. That means complete mass matrix. How we can find it out? Phi transpose M phi. Now, what you need to do, you just need to do the matrix operation and you find out the normalized mass matrix 600 0 0 1200. Now we have the first mode shape. What is from this modal matrix we can easily extract the first mode. What should be the first mode? 0.5 and 1. What should be the second mode? 5 2 minus 1 and 1. Now we need to normalize with respect to the mass. So what will be the normalized mode shape with respect to mass? It's nothing but your phi vector divided by your under root of phi n transpose m phi n. That means this component. So phi 1 was there, 0.5, 1 and under root of 600. You will get the normalized mode shape for first mode. Similar way, you will get the normalized mode shape for the second mode. Now, continuation of this problem. Here, the mass and stiffness matrix of a MDF system is given. Again, the mode shape matrix is also given and the force is also given. Calculate the modal frequencies for two modes. Look, this equation. Few minutes back, I told you like phi n transpose k phi n ultimately leads you to omega n square. If the matrix, this phi and this phi is mass normalized mode shape. So what you need to do is very simple problem. How we can find out the omega square? You just need to do phi m transpose k phi n. And if you solve it, you will get the value of omega square. So practice this kind of problems very carefully. And you need to recall the formula in a way that on that particular time frame this formula will hit to your mind, right? Now for the generalized forces also we can find it out, like force related. For the force vibration case, whatever we have seen, calculate the generalized force. Already the force vector is given. So what is the generalized force? Fn is nothing but, or Fn of t is nothing but phi n of t in bracket your that ft whatever is given. So already phi n, the mass normalized mode shape, we get phi n for the first mode. We have phi 1, we have phi 2 for the second mode, and we have the ft values, the vectors of ft is given as like 25 sine 20t and 10 sine 20t. So multiplied by your phi 1m multiplied by phi 2m will give you the mass normalized or the normalized general forces or generalized forces, or more precisely we can say the generalized forces corresponding to the nth natural frequency or the generalized forces acting on the nth mode. Now the series of question comes from here, like just focus on it. The first question, like how probably how they can project this kind of question. The first question, one question will be given like this: the diagram and the and your system will be given, and they will ask like solve the series of question. But in my opinion, they will not go to 3-DOF system. They will stick to 2-DOF system, because for the 3-DOF system, solving the characteristic equation is like little painful. Yes, right. We need to find out the three roots. It will take more than half an hour, more than 45 minutes. If you have calculators with you, then only. So I think they will stick to 2-DOF system, and solving 2-DOF system is very easy. To use that Sridhar Acharya formula, how to incorporate it and how to get the roots, you just need to figure it out. So I think this is the problem related to your current assignments, right? That's why I have added it. But to show you the continuation, right? If you missed one part, previous steps, then all the problems will, all the solution will be wrong. So here for the 3-DOF system, again, what you need to do, you need to formulate the mass matrix. It's diagonal M1, M2, and M3, and you need to formulate the K matrix. Like here, Bob, you have asked why we multiplied by 2. Like here, for the diagram, they have given K1, K1. For both the column, they have defined K1 and K1, K2, K2, K3, K3. That means we need to multiply it with 2, because we have two columns on each story. That's why, look, in the K matrix, this is multiplied with 2. Okay. Now, for a system,
Right.
if, yeah, yeah, tell me.
Okay, I said all right.
Yeah. And if only K1 and K2 is given for this two story, then, and that each word is not there, then you can stick with that. That K1 is the complete stiffness of the first story, and K2 is the complete stiffness of the second story, right? So now what you need to do? You need to take the pen and solve this characteristic equation. After solving the characteristic equation, you will get omega 1, omega 2, and omega 3. Although they asked for the first natural frequency, but you need to solve 3. So in my opinion, 3-DOF system will not given, but 2-DOF system, omega 1, you need to learn how we can easily get the omega 1 using pen and paper and using your Siddhartha formula on screen calculator. You need to practice it. You need to sit and practice until you get the correct equation with correct time. If you are serious with this exam, then only. Otherwise, you can plan accordingly. So once we have this omega 1, now they will ask calculate the mode shape. Yeah, calculate the mass normalized fast mode shape. Calculate the mass normalized fast mode shape. So how we can calculate it? So we have the omega 1 square. We have our characteristic equation where we know what is the value of the K matrix, what are the values of the M matrix. We can easily find out the phi 1. Now this phi 1 will contain your phi 1 1, phi 2 1, phi 3 1. These three. That means you will have three simultaneous equation what you need to solve. Okay. So how we can calculate? First you need to calculate that phi 1. I have not added the calculations, just directly get the values from MATLAB. So lazy kind of person. So you need to solve them on pen and paper. Just just recall how we are normalizing the modes. Like maybe the modes will be given, omega and modes will be given. You don't need to make the calculation, but you need to recall what should be the formula for normalize the mass, what should be the formula for getting the mass normalized mode shape, and all these things. Let's say we have this phi 1 matrix and M matrix with us. Now what is the uh, mm, way to get that phi normalized mode shape? We just need to do what? That phi 1 under root of the phi 1 transpose M phi 1. So what do you need to do? We need to calculate this M1 first. So M1, how we can calculate? Phi 1 transpose M phi. Now this vector operations, phi 1 transpose M phi, these vector operations are quite tricky also. Many times if you are not with your full conscious, there are more probabilities to get the calculations wrong. So please pay attention and solve whatever problem I have given here, and the assignments problem, just solve it by yourself. you are getting the results on time, just see and check you are getting the results on time or not. You are getting the results on time or not. You are getting the results on time or not. Okay. So after calculation, we can get the mass normalized mode shapes. Okay. For the 2-DOF system also, we have seen how we can calculate the mass normalized mode shapes. The series of questions from 2-DOF system, whatever I have given here. Uh, here, this also you can do the mass normalization thing also with them. So here I have done the mass normalized part. You have the mass matrix, you have the stiffness matrix. You can do the normalization and check the results. Great. Here one more example is there, like how we can get, like, determine, just focus on this problem, then I'll go to that problem also. Determine the natural frequency and modes of the system and normalize the modes so that Mn should be 1. Now maybe the question may be cast like this, like your phi 1 is given for this system, say 1 and 1 by 3. Okay, the mass matrix is also given, say for example 20, 18, 0, 0. Now they will ask, like phi 1, and they will give it phi 2 also, say 1 and minus 1 by 3, and they will ask to normalize the mode shape in such a way that Mn should be equals to 1. That means what they are asking for, Nandalal, what they are asking for? They are asking for the mass normalization, right? So how we can do it? If phi is given, phi 2 is given, if M is given, what we need to do to normalize our phi 1? Bob, quickly. Phi 1 divided by under root of phi 1 transpose M phi 1. You will get the mass normalized matrix. Yes?
Yes, just you explain, sir, this question,
Yeah.
this type
No,
of question.
yeah, is this type of question, why I am stick to it, like they might ask, here are the questions. Okay, here are the answers, like what should be the first. No, I am discussing again why, because either they can ask, like, do the mass normalized mode shape or get the mass normalized mode shape, or they will ask normalize the mode shape such that Mn should be equals to 1. Okay, same kind of questions, but little bit of change in the expression. Okay, so let's go to that portion also. And for the model, Rayleigh and Caugh damping model, which kind of question we will also discuss.
Questions, sir, questions. What about the initial first to 3 weeks, sir? Will be there or not?
Yeah, what I didn't get your point.
Questions from first to 3 weeks, 4 weeks. It will be there or not?
Yeah, obviously we will actually solve these problems on 14th. Okay, today we are stick with that MDF system. On 14th I will, address all kind of questions, don't worry. Yes, obviously for from first to 3, from all the weeks, the question will be there. And the structure of the question, I haven't made go through their website, but still, like 35 to 40 question will be MCQ and MSQ 1 mark question, and then come 2 marks question around 20 to 25 marks, and then rest will be for 3 marks question. We are just discussing the 3 marks question, what should be the structure of that, although we will discuss on that 14th also, no issue. But yeah, from all the chapters from the SDF system, obviously more than 40% of the question will come from the SDF system. Okay.
MDOF system, sir.
Yeah, 40% from the MDF system and 40% from the SDF system,
Okay.
definitely. Okay, so we are discussing the uh, possible questions, so which we can which we need to, uh, focus more focus. Okay, like here we talked about the participation factors. Now this kind of questions may ask, like, we'll go into the damping model later, little later. Let's stick to this problem. So What this problem says, force acting on the first and second and third floors are given. Like we have three DOF systems, and corresponding to first floor, second floor, and third floor, the forces are given. So this is F3T is given, F2T is given, F1T is given. Now calculate the absolute value of generalized force for first and second modes using mass normalized matrices. Okay. So how we can get it? Let's say we found out the mass normalized first mode and second mode. It's a continuation of a question where we already defined what is the mass normalized first mode and mass normalized second mode. That three-top system what we have solved a few seconds before, that W1 comes as some root over of something. That continuation of this problem. Just I will show you. I forgot where I put that. Yeah, for this system. So omega 1 we have found out. On the next page we have found out the mass normalized first mode shape, and let's say in this question also the mass normalized second mode shape is given. So I have calculated using MATLAB, so these values are okay, no issue, but still you need to check it. So to showing the purpose of showing this problem is like how we can get the generalized forces. Generalized forces means already you have solved one problem related to two DOF system. Now for the three DOF system it will be Fn of t should be equals to phi 1 of t, and phi 1 that should be mass normalized multiplied by your F1 of t, and for F2 of t similarly you need to multiply the mode shape mass normalized mode shape 2 with that. So this is the first mass normalized mode shape. This is the vectors of the generalized forces F1, F2 and F3. This is again F2T. These are the generalized forces, and you will find out what should be the generalized force for first mode with respect to the normalized mass, normalized Morse matrix, and what will be the values of the generalized force with respect to the second Morse matrix. Get it? So this kind of problems also can come. Like this problem can be casted like this. They will ask, okay, this is my M matrix. M matrix they will give the K matrix. Okay, they will give the M matrix, they will give the K matrix, and also they will give the phi matrix. Phi matrix. Okay, you don't need to calculate anything. Now they will ask like, what is the value of this normalized forces? So what you need to do first, if the question formulated like this, M matrix, K matrix, modal matrix, all are given, and also this force vector F is given. Now they ask calculate the generalized force for, let's say, first mode. What you need to do? Tell me. If like instead of solving this problem, if they give you the M value, K value, phi value, F value, and then they ask for the generalized force, what will you do? First, what you need to do? First, you need to find out the Mn, right? And then you need to find out the phi 1m normalized mode same matrix with mass phi 2m, and then you need to make the calculation for phi 1 of t is nothing but phi 1m into your force vector. For F2t you will get phi 2m into F2 of t. Okay, got it? Now continuation of the same problem. Okay, continuation of the same problem. Calculate the absolute value of modal participation factor. What I said, you need to recall the expression for the modal participation factor, pk or qk, whatever you want to define, phi n transpose m u or j. So here the influence vector is given, instead of giving you the initial condition, divided by phi n transpose m phi n, right? So form modal participation factor or from the participation factor itself, this kind of questions can come. So to solve this kind of question, what you need to do, first you need to have your phi 1, you need to have your phi 2, then you need to have your influence matrix or influence vector J. So once you have all these things, what you need to do to find out the first mode, we can find out P1 is equals to phi 1 transpose M into J, phi 1 transpose M phi. So you have the M matrix. M is nothing but is given 1800, 1600, 1200. This matrix is given. Influence vector is given. You just need to do the do the matrix calculation. Okay, tell me one thing. On the on-screen calculator, can we calculate the matrix operation directly? Actually, I haven't explored this. Like using normal calculator, we can easily solve this matrix operation. Using this type of calculators, we can easily, go for solving this kind of problems easily. Like you just need to define the matrix and then do the equation. So, is there any kind of option available on the on-screen calculator? I haven't explored yet. I'm just asking you. Have you explored it?
No, sir, I have also not explored so far, sir. Okay, I will try. I will see if something is there.
Because at the end you need to do this calculation, make it simplify, then only you will get the result. So this
But
calculation,
normal calculator and scientific calculator, both options are coming, sir. But in scientific calculator, whether matrix solution is possible or not,
yeah, matrix solution using the scientific calculator, matrix solution is possible, matrix and vector
possible.
solution.
But whether it is there in our monitor PC, means computer PC or not, that
Computer PC I haven't explored now. From using this physical calculator, I know how to solve it. But on the on screen, I haven't explored. I'm just asking like you explore it. If the option will is there, then the way will be similar. I will explain the way how you can do it using this kind of calculators. If they are same there, then I can explain how we can do it easily. Or else I will also explore. I will also explore these things. Okay. So for the second mode also, now for the third mode, if they ask for the third mode, you can do it for the third mode also. So P3 will be nothing but phi 3 transpose mj divided by phi 3 transpose m phi 3. Okay. So by this way, you can calculate the values of the participation factor. Now for a, let's say for a two-DOF system, instead of giving the influence matrix, they giving the initial condition. Say for example, u is equals to nothing but 0 and 1 or 0 or 0.01 something. So you need to do the calculation similar way, but your size of the vector and matrix will reduce. That will like take less time. Okay. Now like for the same three-story building, we also have discussed different kind of modal combination rules, right? Say say u11, this one for u22. Again we have seen that u21, u12, u22, and for the modal combination rule, we have seen that we have SRSS, we have absolute sum, we have CQC, right? To combine them. Because we have seen that the maximum responses or the maximum nodal responses will not occur at same instant of time, right? So to combine them, we have different kind of rules. So that rules are very handy. Once you have like u1 or x1 values, what is the displacement or the modal displacement corresponding to the first mode? Let's say here given as 5.75, 7.24 and 10.54 for the first mode, for the second mode, and for the third mode also given. Now they want you use the SRSS rule. That means sum of square of all the parts. So what you need to do to find out that x max, you need to make square root of 5.75 square plus 3.26 square plus 1.85 square. Again on the second element, that will be under root of 7.24 square plus 4.86 square plus 2.36 square. And for the third element, under root of 10.54 square plus 5.15 square plus 3.74 square. You will get the values, right? And for the absolute sum, you just need to take the absolute value. So they will not ask for the absolute sum, they will ask for SRSS if given. Now, few more questions related to the damping models. Very important. Related to the damping model. And obviously, 3 to 4 marks will come from these damping models. Damping models mean damping models in the multi degree of freedom system. So we have two kind of damping models. So before going to the damping model, let's solve some MCQs. Like for a 5 degree of freedom system, if the natural frequencies are given omega 1, omega 2, omega 3, omega 4, omega 5, what should be the sequence? Omega 1 should be less than omega 2, what should be less than omega 3, should be less than
Yeah.
omega 4, and like that. So you should recall the sequence. Okay. Now in classical damping I will just explain. So already we have explained, like to use the classical damping formulae, we need to have the symmetric damping matrix, like all the roots should be positive and real, that condition should be satisfied, right? Now modal stiffness matrix of a MDOF system, it's always diagonal, right? Modal mass matrix, what should be the modal mass matrix? If asked, what should be what is the value of the modal mass matrix? It will be identity matrix, it will be non-zero matrix, it will be skewed matrix, and all these things. So it will be a identity matrix, right? Modal mass matrix. And right, modal stiffness and modal damping matrix will be diagonal always. Okay, now let's quickly go through these damping models and solve few problems related to damping. So first we have this model we call the Rayleigh damping model, or we call it a classical damping model. So we already explained all this part. So to use that model, this criteria have to be fulfilled. Like C M inverse K should be K M inverse C. That means all roots should be positive and real. Then only we have this kind of symmetric matrix, and our formulation will be aligned with the calculations. So here we have seen that for the Rayleigh damping model, we have one mass dependent property or the parameter, and one is the stiffness dependent parameter. And once we have solved all these things, we have seen that mass proportionality, that A naught, which actually define the mass proportionality, is directly proportional to your omega n natural frequency. And for the stiffness proportionality, we have seen that omega or this A1 is inversely proportional to your omega n, right? And after solving all these things, we have summed up into this model. You need to recall this model. C is equals to A naught M plus A1 K. This is the Rayleigh damping or the classical damping model. So after all, what do you need to recall? What is the structure for the damping in Rayleigh damping model? Zeta n. Zeta n is nothing but A naught by twice omega n. From where we are getting, we have calculated A1, we have calculated A naught, and we have found out what is the values of this, and we have just equate in this equation. So zeta n is nothing but A naught by twice omega n, A1 omega n by 2. That means A naught is directly proportional to omega 1 n, and A1 is inversely proportional to omega n. And the structure will look like 1 by omega I A naught, 1 by omega j A1 is equals to, this 2 will come to this side, 2 into zeta 1 zeta 2. So from this formulation, obviously the problems will come to your final exam. So you need to recall this formulation, and you need to learn how you to solve these equations easily. So here I have explained how to solve for entire problem. That means if for the first two modes, the damping is given. For the third mode, we can easily calculate the damping ratio using the Rayleigh model. So for that, what we need to do, we need to first calculate the mode shapes and all these things. So that things will be given in your formula. So for example, this three-story building have 400, 400 and 200 kg mass. They have stiffness for the first story, this stiffness for the third story, and stiffness for the second story, same. Now, for the first two modes, the damping ratio is given as 5%. Zeta 1 is given as 5%, and also zeta 2 is given as 5%. We need to calculate what will be the value of zeta 3 as per Rayleigh damping model. So what we need to do, first we need to find out the omegas. That means what should be the natural frequency. So 12.57 is the first natural frequency, this is the second, this is the third natural frequency, and corresponding to natural frequencies, this is the first mode shape, this is the second mode shape, and this is the third mode shape. Now once we have all this information, what we need to do, we need to find out the coefficient of this thing. That means zeta n is nothing but a naught by 2 1 by omega n plus a1 by 2 omega n. In a vector or matrix form, we can write it down 1 by omega 1 1 by omega 2, because omega 1 omega 2 is given. What we need to find out, a naught and a1. Once we found out a naught and a1, we can easily use that formula. C is equals to uh, a naught m plus a1 of k. So here a naught and a1 is given. We can easily formulate what will be the value of zeta 3. Zeta 3 is nothing but a naught by 2 1 by your omega n will be omega 3 plus a 1 by 2 omega 3. Now just put these values like 2.1 into 10 to the power minus 3 divided by 2 into omega 3. What was the value of omega 3? Here 46.3. So 46.3 plus a1 value, already we have found out this 0.9165 divided by 2 into omega 3, 46.3. You will find out the value of zeta 3. In similar way, these problems are given like here. The Rayleigh damping coefficients are, the coefficients are already given. If not given, how you can calculate the coefficients? 1 by omega 1 omega 1 1 by omega 2 a1 sorry a0 a1 is equals to 2. You need to recall this zeta 1 zeta 2 by this way. That means in a way you need to just recall that zeta is equals to this formula or this, or there are simple version like I know a0 is directly proportional to omega 1 and a1 is the indirectly proportional to this. So I can easily form it. So if you multiply them and form the equation, you will get zeta 1 is equals to a naught by omega 1 plus a1 omega 1, and this 2 will be there, right? So 2 divided by 2. Okay, so this formulation of the classical damping you must recall. One problem obviously will come, 3 marks 2 marks, whatever it is, it will come. So how we can calculate it for the third mode? So we know omega 3 is given, third mode the frequency is given, otherwise you need to calculate it again. But if it is with some extension question, like extension of some question where you need to calculate the omega first and then all need to do the calculation, then other thing. But for this damping model, I hope all the natural frequencies will be given. You just need to calculate what will be the damping ratio or what will be the C matrix. In a way you need to form it. So here it's pretty straightforward. Zeta n, you need to find out zeta 3. So you have the value of a1 like 1.1 divided by 2 into omega 3 is given 45 plus a1 value is given this 1.8 into 10 to the power minus 3 divided by 2 multiplied by 45, and you will find out the value 0.0527. That means nearly 5%, 5.27%. Okay, obviously this kind of question will come. Now here same kind of question, what is given? The natural frequency of two modes of a two-story is given. W1 is given as 14 rad per second, W2 is given as 36 rad per second, right? Calculate the value of Rayleigh damping coefficients such that the damping ratio is 5% for the first and second modes. So what you need to do, you need to calculate A0 and A1 provided your zeta 1 is equals to zeta 2 is equals to 5%. We can calculate it because we know the relation between zeta 1, A1 and omega 1. So A0 by twice omega n plus A1 omega n divided by 2. Now you can easily calculate, all the values are given, like zeta value is given. So for the zeta 1 we need to write one equation. Zeta 1 is equals to a naught by twice omega 1 plus a1 omega 1 by 2. And also for zeta 2 we need to write same equation, 2 omega 2 plus a1 omega 2 by 2. Now from this equation you can easily calculate what should be the value of a0, what should be the value of a1. Great. So from the classical damping matrix like this should be a diagonal matrix. For a classical damping, it should be symmetric matrix. About the frequencies, you understood like which kind of question may come. So I hope like you have now little bit of understand from the MDF system which kind of question may come. Yes or no? We have few more questions left. We will solve it.
Yes, it's okay.
Okay. So what you people need to do for the exam is like you need to practice how you can solve this within that time, because the time constraint is the biggest constraint over there. If you can recall and remember all these things, then also the time constraint will be there. Now tell me, the modal stiffness matrix of a MDF system is obviously diagonal. A structure is assumed as a classically damped, then damping matrix is symmetric matrix. And in a classical damped MDF system, the modal damping ratio of mass proportional damping. Look, mass proportional damping. क्या होता है mass proportional? Which is the mass proportional damping? It's in classical damping MDF system, the modal damping ratio of mass proportional damping. So look into this equation, zeta n. So mass proportional is this, right? So the mass proportionality is directly or inversely proportional. Tell me. This mass proportionality, that zeta n, for the mass proportionality they have asked for the zeta n. So for the mass proportionality we can write zeta n is equals to a naught by twice omega n. That means zeta n is inversely proportional to omega n. But these constants, if they constants, the mass proportionality constants, then it's directly proportional to this. Okay. Okay, one more model we have, Caugh damping model, but I think that Caugh damping model is not covered during your course. Is it covered? I have explained different questions related to that Caugh damping also. You can go through them, but I feel that this is not there, right? In your course instructor haven't covered that thing. So the thing which is not covered during the course, the question will not come from there. Now here for this question is like related to the MDF system whichever we are solving. So here also for the this system, for this system continuation of this problem, if we look into this problem, like calculate the value of Rayleigh damping coefficient such that damping ratio is 5% for the first and second modes. Again they asked for this. So like for this system, for the three-dop system, we have solved omega 1 and omega 2 is equals to this value, or the omega 1 and omega 2 values will be given. Okay, now what you need to do, that eta or zeta 1 is equals to zeta 2 is equals to 5% is given. What you need to do, you need to calculate the value of a0 and a1 such that zeta 1 and zeta 2 will be 5. That means what you need to do, Rayleigh damping model, we know zeta 1 is equals to a naught by twice omega 1 plus a1 omega 1 by 2, and also zeta 2 is equals to a naught by twice omega 2 plus a1 omega 2 by 2. Now you need to solve for these two equations. So the first equation this, the second equation is this. After solving this equation, we will get a naught is equals to this, a1 is equals to this. So this is in your current week assignments, and the previous one I have already solved. That was also in some of your assignments. So this kind of question we can easily predict, like this kind of question can come. So you need to, what you need to recall, you need to recall the model first, like c is equals to a naught m plus a1 k, and after solving we found zeta n is equals to a naught by twice omega n plus a1 omega n by 2. You need to recall this formula, then you can easily score 4-5 marks easily. Now again, the continuation of this problem, what it says, calculate the damping ratio for the third mode considering Rayleigh damping. Once you can calculate the value of a0 and a1, and you have the value of omega 1, omega 2 and omega 3, you can easily calculate the value of zeta 3 using the Rayleigh damping model. So omega 3 is given, Rayleigh damping model, say omega 1 is given as something, omega 2 is given as something, and omega 3 is given as 63 rad per second. So omega 1 and omega 2 already you have figured it out. Omega 1 17.56 and 45.16, 17.56 rad per second and 45.18, 45.18. So first what you need to do, you need to calculate a0 and a1. Already you have calculated on the previous slide. We have the values of a0 as this and a1 is this. So what will be the value of zeta 3? It's nothing but a0 by twice omega 3 plus a1 omega 3 by 2. Just put all these values, you will find out the values comes as 0.6.04% for this system. Okay, so this kind of questions generally come from the from the multi degree of freedom system. Yeah, one more thing I left with, like from the energy principle or the variational principle, generally the MCQ type of question will come. I will include them on this next class, which kind of all the MCQs and MSQs probably uh, from the assignments and also out of the assignments also, which is there in your lecture videos, or maybe formulated from the lecture videos. But from the energy principle, we can have questions like formulate the Lagrangian. What should be the Lagrangian look like? This kind of small questions, like you need to just formulate the Lagrangian. Lagrangian we know is nothing but T minus B. That means you need to find out the kinetic energy of the system, you need to find out the potential energy of the system, and then you can formulate the Lagrangian. And you just need to give the input of the Lagrangian. Say for example, here the pendulum system is given, right? And also the kinetic energy and potential energy also, you need to find it out. The coordinate, the generalized coordinate for here is given as theta, and the chord length is given as L, and the mass of the bob is given as M. So how you can find it out? What you need to do, you need to first calculate the T, then calculate the V. How you can calculate the T? It's nothing but a half M into V square, we know. Now for here we need to calculate the V. That means what should be the velocity of this bob, uh, because this will be the bob will experience the angular velocity. So we need to first make it linearize. So V is equals to nothing but we know omega into L, the chord length, and then omega we can easily find it out after deriving it. So once we have do this, so we can find out what will be the T value and what will be the V value. We know the potential energy mgl 1 minus cos theta. Once you figure out the coordinates, you will find out that this value is and this value. So you can find out this scattered, that 1 minus cos of theta. Already we have solved this kind of problem. Please go through this kind of problems where you need to calculate what should be the kinetic energy, what should be the potential energy, and what should be the form of the Lagrangian for these equations. Okay. And this kind of short questions like which formula represents Hamilton's law action principle where T and U represents the kinetic and potential energy of the system. So Hamilton principle we have already discussed that is the first variation with respect to that will be 0. That means del T1 to T2, the first variation, that means T minus U dt should be equals to 0. That means your B option. Similar kind of question like kinetic energy of the system is given is that potential energy, calculate the terms of Lagrangian equation. This here Qi is the general coordinate. Okay, so they have asked for the calculate the terms of Lagrange equation. The terms of Lagrange equation. Lagrange equation. The terms of Lagrange equation means they are asking for d dt of del t by del q1 dot minus del t by del q1 first, and the second one was d dt del t by del q2 dot for the second coordinate minus del t by del q2 is equals to 0. You just need to not equals to 0, you need to find out the values equals to what and equals to what. That means you just need to make the derivation with respect to first q1 dot and q. So first only we have q1 dot component here, so that q component will be vanished. So you just need to do a look for the q dot component. You will find out that this term will comes as this. That means d dt of after doing this, and that will comes as m by 6 q1 plus q2, and this will be value of up with q2 dot. That means what you need to do, you need to recall this formulation of Lagrange equation. Here also let's say function, similar kind of problem, similar kind of, these are like already given in your assignments, and this kind of problems will be there, or this kind of MCQs only will be there in your exam. Like let function is given, integral form of the function is given. Now for first Euler equation, what is the value? So you just need to recall them. Like for the first Euler equation, what the first Euler equation says, that del f by del y minus d dx of your function del f by del y dot should be 0. That is the first Euler equation. What was the second Euler equation? That variation minus the first derivative of this variation with respect to your y or t is equals to 0. Yeah, sorry, y dot and k. I written it wrongly. This the the this one. So what you need to do, you need to recall the variational principle, form of the variational principle. You need to recall the first and second Euler equation and the like form of the Lagrangian equation. That means L is equals to T minus V, that form, and after solving this form, this d dt of del T by del Q dot minus this should be what? So this kind of things, or this kind of small problem can come from the variational principle part. So that's all, like from the MDF system. You just recall them, practice them. I think that will help. Any more suggestions that we can incorporate on the next class? Anything? Like what do you want more? Like how we can proceed it? Any suggestions so that I can incorporate these things and do it? Like tomorrow, Sunday, I can do it easily, and on Monday we have the class, right? So any suggestions, any kind of things like that will be helpful. I will try to incorporate them.
Doing this much is more than sufficient, I think. If you are able to digest these things, now it will be too
Yeah.
much.
yeah, and in a way you need to digest it. You just and there is a process to recall. Like you just need to recall few of the things, and you need to practice. Automatically, your mind will tell you, okay, what is you need to do after that. You just need to be
Okay, sir. We'll
clear.
try our best.
Yeah, practice, practice, practice.
Yes,
If you
yes.
practice in practice, if you tried your best, then automatically, byproduct will be a good exam. Okay. So you need to practice it. All of you need to practice it. And also, if I stop practicing, I will also forget. So that's happened to us,
Yeah,
no?
this is a
So
heavy
your ma-
course.
Yeah. That's a heavy course, and like all the problems actually referred to solve using MATLAB and using scientific calculator. Now using that course within that stipulated time without calculator and MATLAB, it's quite uh, like little bit of tough. But Bob, we have done reliability based structural design.
Oh yeah,
Don't
yeah,
you?
yeah, yeah.
Yeah, that course was 10 times heavier than this minimum. And yeah, minimum.
No,
you
but
you,
you
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 can
you you
sense
you
it.
you did very well on the reliability.
Yeah,
You
that
made the
I was also
course
like
very
how.
very very simple. You did very very well. You made
Yeah,
the course
and
simple,
if
just
that
like
course
you're
can
doing
be
with
done,
this.
and good score can come from that type of courses, then this is very simple. With respect to this course, if I look this course, this is very simple. Like, and you have done this course and you got some good score, right? You send your certificate. I have seen it. I
Yeah,
have
yeah,
followed it.
yeah,
Yeah, but
yeah.
that course was really like how we can proceed for the questions. Like without MATLAB, we cannot think of reliability. But
Sure.
in a way we have done it, and in a good manner. And that course was very very interesting, and for the research purpose, and to understand that the uncertainties and reliabilities associated with any structure, any kind of structure. It can be a rocket, it can be a drone, it can be anything. So we need to perform this kind of exercises for them. So it's okay. That course will also goes well. No issue, no issue. Just practice, practice, practice. All the assignments you have given to
We will
you,
get back on
practice.
our.
Yeah, yeah. When you have exam,
26, sir.
26. Okay, 26
Yeah,
Sunday.
yeah.
So you have, okay, you have 2 weeks. Enough, enough
No,
for
no,
a
13 days, sir. 1 week, 1 day less.
yeah, yeah. That's also enough. Now we are in a mature stage, so that's enough, right?
Mature stage is more problem, sir. Diversion will be more.
Yeah, yeah. That I also admit it. Yeah. But in a way we need to do it. So on the next class, what I will do, I will put all these MCQs like as per how a final question look like in same format, and we try to solve it. Okay, from different kind of
Sir, it is your Monday 10 to 12, no?
Monday 10 to 12. Yeah, 10 to 12, right? 10 to 12 or 11 to 1. I forgot actually. I need to see that.
Mail will
You
come, no, sir. Mail in
Yeah,
the.
yeah. Mail will come. Mail have already come to you, right? So
I
it's
have not seen, sir.
it's from 10:30. Nandal.
Okay,
Nandalal,
okay.
it's from 10:30.
Okay, sir. Okay, thank you.
Okay. You received the mail?
Actually, I have not checked the mail. Once I checked, it was not there. Okay, I will check once again, sir.
Okay, okay. One second, please. You check, and otherwise the link will be same as this. Okay, same link. And please, yeah, give the feedback. You receive some feedback link from NPTEL site.
Yes, sir. Yes, sir.
Yeah,
Okay, we'll fill the
Yeah.
feedback.
yeah. Actually, based on that feedback, my evaluation will be done.
Okay, sir. Okay. No, actually, you have put
Okay.
very nice effort, sir. The way you have taught now, it is very fantastic, sir.
Thank you.
Yeah, yeah.
even
We've done many courses. Your approach to
you can
helping students is totally
open
different.
your cameras. Like you people are senior people, so you can on your cameras.
1 minute, sir.
Like Bob is a senior structural engineer, and Nandalal is also working with ISRO, like some projects you told.
Yeah, yeah, sure, sure.
So hi Bob, how are you?
Very fine, very fine. So
Yeah.
this one I registered for about 5 courses this time.
Okay,
So
which courses?
I'm, I did for responsive soil, which I've written the exam,
Okay,
and then soil structure interaction.
yeah, soil structure interaction is also a interesting course.
Yeah, it's another heavy course.
Not
And
heavy, but
then
yeah, it's quite interesting. Soil structure interaction, uh,
but
the course. Yeah,
you see the notes are a lot.
yeah.
Over
So,
over
it,
60 videos,
and
almost
also
70
completely
videos.
based on the dynamic modeling, right? So,
Exactly.
dynamic
And
modeling.
some structure analysis and some dynamic, some yeah. So because of that, I'm doing this course to get the knowledge and write it in my next
Yeah, in soil structure
registration.
interaction also, when you need to model your soil spring, so you need to consider the dynamic model itself. So
Yes, yes,
yeah.
yes.
So without dynamics, we cannot think of that randomness optimization or the dynamic cases or the vibration. So it's the basic course. Then later on, like soil structure interaction, reliability based design, random vibration, this kind of courses come. So
Once you get all this trade, then I see how the trade can link together to.
Nandalal, can you please mute yourself? Like is echoing there. Okay. Uh, so it's nice like working with you guys. Like you are much more senior than me. But still, you are very good participants, I must say. Like, I must admit this, like, throughout the entire thing. And 2 hours, 2 hours, during that 2 hours, it's like boring to me and much boring to your side who are listening. Like, I'm writing something, it's okay, I can, manage this time, but who is listening, I can understand and I can feel how, like, still you people are, like, managing. Now, I hope you will have a nice exam, no issue.
Sir, you
Good.
made the session interesting. That is why we are 2 hours connected to you, sir.
Yeah, right. Definitely. Then okay, then
Yes,
we will meet on Monday. And if you have any kind of doubts, you can mail me. No issue. My mail ID is on there. So okay, Monday we will discuss all these things. And if you have any kind of doubts, so we will solve on that day.
Email ID, no?
right.
Email ID. How we can get, sir, for your email ID?
Yeah, email ID is here only on the slide. 1 second.
Okay, 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 okay. Slider.
Just 1 second. 1 second. I will give here. Can you see it? p.devasis@iitg.ac.in. So you can mail me. I am quite active there. Any kind of, if you have any kind of doubts related to your projects, if I can help, I will definitely help. Not
Okay, sir.
related to
Okay.
this course, any kind of things, dynamics and all these things related to my background or any research, any area of interest. If I can help, obviously I will provide that.
Actually, I am very beginner in this field, sir. Actually, I told in the start also I am joining this PhD course after my BTech, sir, directly.
Okay.
And after a break of almost 17 years of study, sir.
Yeah, 17 years. It's lot.
That's
And,
tough.
and and like
Yeah.
I really often wonder, like, at this age how you people get the courage and like to do this kind of heavy courses. Like, I still wonder, like, how at that age. uh,
I'm also surprised, sir, how I have selected, sir. But okay, once I am selected, I have to do, sir.
that's why there is a saying, na, age is just a number. All things, this, if you think like we can.
Yeah, yeah.
Yeah.
Actually,
That's
that
very
is the
true.
main motivation for me, sir. I have joined. Now I will continue. Whatever the situation, I will see.
Yeah, and now you are feeling that, yeah, it's quite easy and we can do it easily. And
Yes, but okay. I feel that I myself should be more systematic for this last minute headache, sir.
yeah, that kind of things, and that time frame has changed. So accordingly, you need to change your time frames, and accordingly, all the things will get aligned over time.
Yes. Yes.
So then, okay, nice talking with you guys. We'll
Okay,
meet
sir.
on the next class. Okay, thank
Okay.
you, thank
Okay.
you.
Fine. Thank you.
Thank
Thank you,
you.
sir.
Thank you.
Thank you, everyone.
All right.
Yeah, thank you.
Thank you. All right.